Hello, friend. Welcome to Science for Sleep. There was a time when salt was so valuable that it shaped economies and paid wages. The word salary comes from the Latin salarium, a term connected to payments made to Roman soldiers, linked in part to salt, a simple mineral, traded across continents, carried along dusty roads, stored in guarded warehouses, measured and taxed. What now rests quietly on kitchen tables once determined wealth, travel, and survival. Tonight, we will spend time with this ordinary substance. If you were to look closely at a few grains of salt resting on a dark surface, you might notice their shape. Many form tiny cubes with straight edges and quiet symmetry. This is not coincidence. At a microscopic level, salt is made of sodium and chloride ions arranged in a repeating three-dimensional lattice. Sodium carries a positive charge. Chloride carries a negative charge. Opposites attract, and they stack together in balanced layers. That internal geometry is what gives the crystal its familiar cubic form. Inside each small grain is a precise electrical architecture. And yet salt is not always rigid. Deep beneath the surface of the earth, large underground salt deposits behave differently. Under immense pressure and over long periods of time, solid salt can slowly flow. It does not melt. It does not become liquid in the usual sense. But it moves gradually, rising upward through surrounding rock in structures known as salt domes. Over thousands and millions of years, what seems like a brittle mineral can shift and reshape the layers above it, almost like thick honey pressing upward in slow motion. A solid that flows. What appears fixed can, under the right conditions, move. If you enjoy these quiet journeys, you're welcome to subscribe. And if it feels natural, to leave a comment sharing where you're listening from tonight. It helps others find their way to this calm corner of the world, one sleepy traveler at a time. The quiet continues here, just as it is. When salt touches water, something equally gentle occurs. The crystal dissolves, separating into charged sodium and chloride ions, water molecules, which have slight positive and negative sides of their own, surround the ions and pull them into solution. The solid lattice breaks apart, but nothing disappears. The particles remain, simply dispersed, invisible to the eye. What was once a visible grain becomes part of the water itself. Salt lowers the freezing point of water. That is why icy roads are treated with it in winter, and why seawater remains liquid at temperatures where fresh water would freeze. A small concentration of dissolved ions shifts the behavior of an entire system. Phase changes adjust. Boundaries soften. In the human body, salt is never still. Sodium ions move across nerve cell membranes, creating electrical differences that allow signals to travel. Each thought, each movement, depends on carefully maintained sodium gradients. Blood plasma holds sodium within a narrow range, typically around 135 to 145 millimoles per liter. The body monitors and adjusts this concentration constantly. If it drifts too far, cells swell or shrink as water shifts across membranes through osmosis. Salt shapes the balance of fluid inside and outside every cell. Even tears contain salt. Sweat leaves faint mineral traces on the skin when it dries. The ocean holds salt at an average concentration of about 3.5%, a level that has remained remarkably stable over immense spans of geological time. Rivers bring dissolved minerals from land to sea, and yet the ocean's salinity does not endlessly rise. Systems quietly balance what enters and what leaves. You might picture a calm shoreline at dusk, the surface of the water smooth, reflecting a fading sky. Beneath that surface, dissolved salt moves freely, unseen but active. It influences how currents circulate, how ice forms, how marine life maintains its internal chemistry. It dissolves, it balances, it shapes structure without insisting on recognition. Tonight, we will move slowly through its quiet influence. From crystals to currents, from ancient trade routes to the electrical signals inside the body, from deep underground formations that shift like slow rivers of stone to the small grains that rest unnoticed on a table. Something so common, something so steady. Salt becomes noticeable in a different way when it reaches the tongue. As food touches the surface of the mouth, dissolved sodium ions move into tiny pores on the tongue called taste buds. Within each taste bud are specialized cells that respond to specific chemical signals. Sodium ions pass through channels in these cells, creating small electrical changes that travel along sensory nerves toward the brain. The experience is simple and immediate. Salty. Unlike sweetness or bitterness, which involve more complex receptor systems, salt taste is closely tied to the direct movement of sodium ions. The ion itself carries the signal. When sodium enters these taste cells, it slightly alters their electrical state, and that shift is interpreted as flavor. You might imagine a few grains of salt dissolving on the surface of warm soup. The crystals soften, separate into ions, and spread across the tongue. Within moments, those ions enter channels and create faint electrical signals. The sensation arises not from the crystal itself, but from its dissolved form interacting with living cells. Salt taste has a threshold. Very small amounts may go unnoticed. As concentration increases, perception grows stronger. Yet beyond a certain point, the experience shifts from pleasant to overwhelming. The body responds differently at different levels, suggesting that detection evolved not only for enjoyment, but for regulation. Salt enhances other flavors. When added in modest amounts, it can reduce bitterness and amplify sweetness or savory notes. Sodium ions influence how taste receptors respond, subtly reshaping perception. This is why a small pinch of salt can deepen the flavor of foods that are not obviously salty. The presence of sodium alters the balance of signals reaching the brain. The effect is chemical and perceptual at once. Across evolutionary time, humans developed a preference for salt. Sodium is essential for nerve function, muscle contraction, and fluid balance. In environments where dietary sodium was scarce, individuals who could detect and seek out salty substances had an advantage. The taste system became tuned to notice and appreciate sodium. Early human diets often contained limited concentrated salt sources. Inland environments, especially far from coastal regions, offered few easily accessible mineral deposits. Plants generally contain low sodium levels. Meat provides some, but not always in abundance. The ability to detect salt would have helped guide behavior toward necessary intake. Low sodium levels in the body can trigger craving. Hormonal systems respond when sodium concentration drops. Aldosterone signals the kidneys to retain sodium. The brain increases attention towards salty foods. The desire is not random. It reflects physiological need translated into perception. You might picture a dry landscape where animals gather around a mineral-rich outcrop. Deer, elephants, and other mammals seek natural salt licks, sometimes traveling long distances to reach them. These locations provide essential minerals not readily available in surrounding vegetation. The behavior is steady and purposeful, shaped by internal regulation. Taste, in this sense, becomes guidance. Salt perception helps maintain balance before imbalance becomes dangerous. The body anticipates needs through sensation. The tongue becomes an early detection system for internal chemistry. Even at the level of a single taste bud, structure matters. Each bud contains multiple cells that renew themselves over time. The ability to detect sodium depends on the presence of specific ion channels embedded in cell membranes. These channels respond primarily to sodium ions rather than chloride. The signal begins with sodium movement. A quiet electrical event begins a sensory experience. You might imagine warm bread resting on a table, a thin scattering of salt across its surface. The grains dissolve against moisture, spreading gently. The taste that follows feels immediate and simple, yet it reflects a chain of microscopic events. Ion entry, membrane depolarization, nerve signaling, interpretation. Salt taste is not decoration. It is communication. The system evolved not only to enjoy flavor, but to monitor necessity. The body maintains sodium within narrow limits, and perception assists in that regulation. When levels are sufficient, craving subsides. When levels fall, attention shifts. What begins as a crystal becomes sensation. What becomes sensation shapes behavior. The same sodium ions that carry electrical impulses along nerves now initiate the signals that tell the brain they are present. Salt moves from lattice to liquid, from current to taste, linking chemistry and perception in a steady cycle of detection and response. Long before salt rested in small bowls on tables, it was something sought. In many early human environments, sodium was not abundant. Inland landscapes often provided only trace amounts through plants and fresh water. Rainwater carries almost no dissolved salt. Rivers contain minerals, but at much lower concentrations than the ocean. For communities living far from coasts or mineral deposits, reliable sources of concentrated sodium were limited. The body, however, required it. Sodium supports nerve signaling, muscle contraction, and fluid balance. Without steady intake, internal concentrations would fall. The kidneys can conserve sodium to a remarkable degree, reclaiming most of what they filter. Yet conservation alone cannot replace what is absent. Over time, dietary access matters. This scarcity shaped behavior. Groups that identified natural salt sources gained advantage. Mineral springs, dried lake beds, and exposed rock deposits became valuable sites. People traveled to reach them. Paths formed. Exchanges began. Salt moved across distances because it preserved food, but also because it preserved physiology. You might imagine a dry clearing where the ground is pale and crusted. Animals gather quietly, pressing their tongues against the earth. These are salt licks, natural deposits where minerals accumulate at the surface. Deer, elk, bison, and elephants return repeatedly to such sites. The behavior is not random. It reflects mineral need translated into movement. Salt influences migration. In some ecosystems, entire animal patterns revolve around access to mineral-rich areas. During certain seasons, herds adjust routes to ensure adequate intake. Even predators indirectly follow these paths, drawn by prey that congregate at salt sources. A small chemical requirement shapes landscape-scale motion. The preference for salt is not merely cultural, it is biological. When sodium levels drop, hormonal systems respond. Aldosterone signals the kidneys to retain more sodium. At the same time, neural circuits increase sensitivity to salty taste and enhance motivation to seek it. What feels like desire corresponds to measurable shifts in internal chemistry. In early human societies, coastal communities often had easier access to salt through evaporated seawater or dried fish. Inland communities developed methods to extract salt from brines or mineral-rich soils. Evaporation techniques emerged, allowing concentrated crystals to be harvested from shallow pools. Salt became portable. Once collected, it could be traded. Its light weight relative to importance made it valuable for exchange. Trade routes formed not only for luxury goods, but for necessities. In some regions, salt blocks were transported across deserts. In others, caravans moved between coasts and inland settlements. Salt influenced where people settled. Areas near mineral deposits often supported larger populations. Preservation methods using salt allowed food to be stored for longer periods, reducing vulnerability to seasonal scarcity. A mineral that dissolves easily became central to stability. You might picture a wide plain with faint paths etched into the soil. Travelers moving slowly, carrying goods that include sacks of crystalline salt. The crystals reflect sunlight faintly as they shift within their containers. Nothing dramatic, just steady movement shaped by quiet need. Animals and humans share this pattern. Salt-seeking behavior appears across species. Even insects have been observed gathering on mineral-rich surfaces. Butterflies sometimes cluster around damp soil that contains dissolved salts, absorbing sodium through their proboscises. The mineral travels through food webs in subtle ways. A chemical element guides instinct. Salt scarcity in early environments did not eliminate survival, but it required adaptation. People learned where to look. They observed animal behavior. They recognized that certain soils tasted different. Knowledge passed between generations. Sodium, though invisible in water, became visible in its absence. When intake fell too low, weakness followed. When access returned, stability improved. Over time, taste preference reinforced acquisition. The tongue helped guide survival long before trade networks formalized distribution. Salt, small and crystalline, shaped travel and exchange. A need at the cellular level influenced patterns across continents. From neurons requiring sodium gradients to herds adjusting seasonal routes, the same mineral threads through biology and geography. It connects body chemistry to migration paths, quiet cellular regulation to visible movement across land. A dissolved ion becomes a journey. A crystal becomes a destination. As salt moved across landscapes, it began to shape human systems more visibly. In many ancient societies, salt was not simply a seasoning. It was infrastructure. Coastal communities harvested it by allowing seawater to evaporate in shallow basins under the sun. Inland cultures extracted it from mineral springs or mined it from underground deposits left behind by ancient seas. Once collected, salt could be stored, transported, and exchanged. Its importance extended beyond taste. Salt preserved food. Before refrigeration, keeping meat or fish from spoiling required drawing out moisture. Salt does this through osmosis. When applied to fresh food, it pulls water from bacterial cells, dehydrating microorganisms and slowing their growth. This allowed communities to store protein through winter months or transport it over long distances. Preservation meant stability. In regions where harvests fluctuated, salted foods reduced the risk of scarcity. Fishing communities could salt their catch and trade it inland. Herding societies could cure meat for future use. A mineral that dissolves easily in water became a barrier against decay. Trade routes formed around this need. Across the Sahara Desert, caravans carried blocks of salt mined from deep underground deposits in places like Tagaza. These blocks were traded for gold, grain, and textiles. In Europe, routes linked coastal salt pans with inland settlements. In China, state-controlled salt production generated revenue for centuries. Salt was taxed. In several civilizations, governments imposed levies on salt distribution because demand was reliable and widespread. The ability to control salt meant control over preservation and daily diet. In some cases, resentment over salt taxation led to unrest. Access to a mineral could shape political tension. You might picture a long road stretching between settlements, lined with travelers moving steadily. Some carry textiles, others carry grain. Among their goods are sacks of crystalline salt, faintly white against darker fabrics. The crystals inside each sack are uniform, cubic, formed from the same lattice structure described earlier. Their internal geometry remains unchanged as they move from coast to countryside. The word salarium, linked to Roman soldiers, reflects salt's value in daily life. Though historians debate the exact nature of payments, the linguistic connection shows how closely salt was tied to compensation and labor. A mineral associated with preservation and necessity became linked with livelihood itself. Salt also shaped settlement patterns. Communities often formed near reliable sources of mineral extraction. Evaporation pans required flat land and steady sunlight. Mines required access to underground deposits. The presence of salt could influence where roads were built, where markets emerged, and where populations concentrated. In colder climates, salt preservation extended the storage of dairy products and meats. In warmer regions, it allowed fish to travel inland without rapid spoilage. Salted and fermented foods developed distinct textures and flavors across cultures, reflecting variations in climate and available ingredients. Fermentation, in particular, depends on controlled salinity. Salt suppresses harmful bacteria, while allowing certain beneficial microbes to thrive. This balance produces foods such as cured vegetables and preserved fish sauces. The concentration must be sufficient to prevent spoilage, but not so high as to halt microbial activity entirely. A small adjustment in salt concentration determines outcome. You might imagine a wooden barrel resting in a dim storage room. Inside, vegetables are submerged in brine. The liquid appears still. Dissolved sodium and chloride surround plant tissues, drawing water outward and creating an environment where selected microbes can persist. Over time, texture shifts. Flavor deepens. The transformation unfolds gradually, shaped by invisible ionic gradients. Salt influenced architecture as well. In some regions, entire towns were built near mines carved into ancient deposits. Underground chambers cut from halite sometimes appear translucent when illuminated, walls faintly glowing from embedded crystals. These deposits formed hundreds of millions of years ago, remnants of evaporated seas compressed and buried. A grain held in the hand may once have been part of an ocean older than many mountain ranges. From preservation to taxation, from trade routes to settlement sites, salt shaped economic and social systems. It linked cellular necessity with communal organization. The same sodium ions that support nerve signals moved through markets and across borders. A mineral dissolving in water also dissolved into culture. Its influence spread quietly, steady and persistent, connecting bodies, food, land, and exchange across centuries. When salt touches fresh food, a quiet shift begins. At the surface of a piece of meat or a cut vegetable, water is present inside cells and between fibers. Bacteria, too, depend on water to grow and reproduce. When salt is applied, it does not act as a poison in the usual sense. It changes the balance of water across membranes. Osmosis moves water toward higher concentrations of dissolved particles. When salt crystals dissolve on the surface of food, they create a region of higher solute concentration outside microbial cells. Water inside those cells moves outward in response. As water leaves, the cells lose volume. Their internal processes slow. In many cases, growth halts entirely. Salt preserves by drawing moisture away. The same principle affects the food itself. Water moves out of muscle fibers or plant tissues, altering texture. In cured meats, this gradual dehydration concentrates proteins and changes firmness. In vegetables placed in brine, salt softens cell walls and creates an environment where specific microorganisms can thrive, while others cannot. The process is selective. High salt concentrations inhibit many harmful bacteria, yet certain lactic acid bacteria tolerate moderate salinity. In fermented foods, salt creates a controlled environment. Beneficial microbes convert sugars into acids, lowering pH and adding another layer of preservation. The outcome depends on concentration, temperature, and time. A balance of variables shapes flavor and safety. You might imagine a wooden table where a piece of fresh fish rests beneath a scattering of coarse salt. Over hours, the crystals dissolve into a thin film of moisture drawn from the flesh. That moisture mixes with sodium and chloride, forming a brine that seeps slowly into the tissue. The surface becomes firmer. The scent shifts subtly. Nothing dramatic occurs, yet the microbial landscape changes. Without refrigeration, this method allowed communities to extend the life of perishable foods. Salted fish traveled inland from coastal regions. Cured meat sustained populations through seasons when fresh supplies were scarce. Preservation reduced uncertainty. Salt does not eliminate all life. It reduces water activity, the measure of unbound water available for microbial growth. Many bacteria require a certain water activity threshold to reproduce. By lowering that threshold, salt limits their ability to multiply. The effect is physical rather than chemical toxicity. Texture changes reflect this water movement. As water exits cells, proteins denature and reorganize. In meat curing, salt interacts with muscle proteins such as myosin, affecting their structure and ability to retain moisture. The final product feels denser, more cohesive. In pickled vegetables, the firmness may shift depending on concentration and duration. You might picture a ceramic jar filled with sliced cucumbers submerged in brine. The liquid appears clear and still. Within it, dissolved sodium and chloride surround plant cells. Over time, water moves outward, and microbial populations adjust. Tiny bubbles may form as fermentation progresses. The transformation unfolds without noise. Salt becomes a boundary. It defines inside and outside at the level of cells, just as it does within the body. The same osmotic principle that regulates fluid balance in blood now regulates moisture in preserved food. The physics remain constant. Even dry curing relies on slow diffusion. Salt placed on the surface gradually penetrates inward, following concentration gradients. The rate depends on thickness, temperature, and salt concentration. Patience becomes part of the method. A mineral guides time. Preservation also influenced flavor development. Controlled salinity allows enzymatic processes to proceed without rapid spoilage. Proteins break down into amino acids. Fats change gradually. The result is depth of taste shaped by ionic presence. Salt's role in preservation links directly to its behavior in water. Dissolved ions alter water movement. Altered water movement alters microbial survival. Altered microbial survival alters food stability. A chain of cause and effect extends from crystal to culture. You might imagine shelves in a dim storeroom, lined with cured meats and jars of preserved vegetables. The air is cool, the surfaces are dry. Within each container, sodium and chloride remain dispersed, continuing to regulate moisture and microbial activity. A small grain scattered on fresh food becomes structure against decay. Salt shifts equilibrium. It draws water, shapes texture, slows growth, and extends time. The same ions that carry electrical signals now carry preservation through physical law. From nerve impulse to fermentation jar, the principle remains steady. Water moves. Salt defines the direction. Beyond the table and the storeroom, salt gathers at a much larger scale. The ocean holds an average salinity of about 3.5%, meaning that in every liter of seawater, roughly 35 grams are dissolved salts. Most of that mass is sodium and chloride, though other ions such as magnesium, calcium, and potassium are present in smaller amounts. The concentration may vary slightly between regions, but across vast stretches of open ocean, it remains remarkably consistent. This consistency is not accidental. Rivers carry dissolved minerals from land into the sea. Rainwater falls onto mountains and soil, absorbing small amounts of dissolved rock as it flows downhill. These ions travel through streams and rivers until they reach the ocean. Over time, This process would seem to suggest that the sea should grow steadily more saline. And yet, it does not increase without limit. Processes within the ocean remove salt at nearly the same rate it is delivered. Some ions are incorporated into marine organisms, forming shells and skeletons that eventually settle to the seafloor. Others become trapped in sediments or crystallize in restricted basins, where water evaporates faster than it is replenished. Over geological time, tectonic processes subduct portions of ocean crust, carrying mineral deposits back into the Earth's interior. Input and removal balance one another. You might imagine a wide horizon at dusk. The surface of the water appears uniform, a continuous sheet reflecting the fading sky. Beneath that surface, dissolved sodium and chloride drift freely among currents that move slowly across entire basins. The water feels continuous, but it carries within it a mineral signature shaped by millions of years of exchange between land, atmosphere, and sea. Why are the oceans salty in the first place? Early in Earth's history, volcanic activity released gases and minerals into the atmosphere and surface waters. As rain fell onto cooling crust, it dissolved ions from rocks. These ions accumulated in the earliest seas. Over immense spans of time, cycles of weathering and deposition established a steady state. The ocean became a reservoir. Evaporation plays a role as well. When sunlight warms the ocean surface, water molecules escape into the atmosphere as vapor. Salt does not evaporate. It remains behind. Clouds form from this distilled vapor and return fresh water to land as rain. Rivers then carry new dissolved minerals back toward the sea. A loop, steady and repeating. You might picture sunlight warming a shallow stretch of coastline. Water slowly recedes from a tidal pool, leaving behind a thin crystalline film along the edges of stone. Those crystals represent only a small local example of a global process. At planetary scale, evaporation concentrates salts, while rainfall redistributes water. Despite this ongoing exchange, the average salinity of the ocean has remained relatively stable for tens of millions of years. This stability supports marine life adapted to specific ionic conditions. Fish regulate internal salt concentration through specialized cells in their gills. Many marine organisms depend on the surrounding salinity to maintain osmotic balance. The ocean's salt is not evenly mixed at all depths. Temperature and salinity together determine density. Saltier water is slightly denser than fresher water. In polar regions, when sea ice forms and excludes salt, the surrounding water becomes even saltier and heavier, sinking into deeper layers. This movement contributes to large-scale circulation patterns that transport heat and nutrients around the globe. A dissolved ion influences planetary motion. If you imagine a cross-section of the ocean, layers form not from visible boundaries, but from subtle differences in temperature and salt concentration. These gradients guide currents that may take centuries to complete a circuit. The mineral content of seawater shapes how energy moves across hemispheres. Salt connects rainfall to river, river to sea, sea to cloud. It gathers slowly and disperses slowly. It shapes freezing points, density, and life itself. The same sodium and chloride that moved through a curing jar now drift through waters that cover most of the Earth's surface. What appears as a simple expanse of blue holds within it a quiet mineral architecture, steady and enduring. the ocean does not announce its salinity. It carries it quietly in every wave. When sunlight warms the surface of the ocean, water begins to rise. Molecules at the surface gain enough energy to escape into the air as vapor. They leave behind what they cannot carry with them. Sodium and chloride do not evaporate under ordinary conditions. They remain dissolved in the sea. What lifts into the sky is nearly pure water. Clouds form from that distilled vapor. Rain falls over land, and the water that returns to soil and stone begins its quiet work again. As it moves across rock surfaces, it dissolves small amounts of minerals. Sodium, calcium, potassium, and chloride enter the flow. Streams gather into rivers. Rivers move steadily downhill. The minerals they carry are invisible in motion, yet measurable. Eventually, they return to the ocean. The water cycle does not simply circulate water. It redistributes dissolved material. Evaporation separates salt from water. Rainwater, nearly free of dissolved salts at first, collects new minerals as it moves across continents. Over immense spans of time, this process has carried vast quantities of dissolved rock into the sea. You might imagine rain falling on a mountainside. The droplets appear clear. As they seep into cracks and flow over stone, they interact with minerals embedded in the rock. Tiny amounts dissolve. The flow becomes a faint solution, still transparent, yet chemically changed. That water joins a river, then moves toward the horizon. Where evaporation exceeds rainfall, salt accumulates. In arid regions, shallow lakes may gradually lose water to the atmosphere faster than it is replenished. As water volume decreases, dissolved salts become more concentrated. Eventually, crystals begin to form along the edges. Salt flats emerge, wide, pale surfaces that reflect the sky like mirrors when wet. These flats represent concentrated remnants of the water cycle. In geological history, entire inland seas have evaporated under shifting climate conditions. When water disappears and leaves behind thick layers of salt, those deposits may later become buried under sediment. Over millions of years, pressure compacts them into solid halite beds. You might picture a vast, shallow basin under intense sunlight. The water retreats slowly. The surface becomes increasingly saline. White crystalline crust forms along the margins, expanding inward as evaporation continues. When the basin dries completely, a broad salt plain remains, textured and bright. Evaporite deposits record this process. Geologists study layered sequences of sediment and salt to understand past climates. Alternating bands of halite, gypsum, and other minerals reveal cycles of evaporation and refilling. Each layer represents a period when water balance shifted. The same principle operates today at smaller scales. In coastal salt pans, seawater is guided through shallow ponds. As the water evaporates under sunlight, salinity increases until salt crystallizes. The crystals are harvested, washed, and dried. The process depends on careful timing and controlled flow, but it reflects a natural mechanism driven by solar energy. Evaporation leaves salt behind. Rain returns fresh water to land. Rivers carry dissolved minerals back to sea. The cycle continues. You might imagine a quiet desert basin at dusk, the surface of a salt flat glowing faintly in fading light. The air is dry. The ground beneath reflects a pale sky. These crystals once drifted invisibly in water. Now they rest as solid evidence of evaporation's work. The water cycle shapes more than rivers and clouds. It shapes mineral distribution. It connects atmosphere to rock, rock to river, river to sea, sea to sky. The same sodium and chloride ions that move through oceans and bodies now rest in layered deposits, waiting for pressure or weathering to set them in motion again. Salt does not travel upward with vapor. It remains grounded, and in remaining, it accumulates, records, and defines landscapes across time. From rainfall on mountain stone to bright salt plains under open sky, the cycle continues without urgency, guided by sunlight and gravity. Water moves, salt stays. Together, they shape the surface of the earth. Beneath the surface of the earth, salt rests in layers that were once oceans. Halite, the mineral form of sodium chloride, forms when seawater evaporates and leaves its dissolved salts behind. Over geological time, entire inland seas have dried under shifting climates, depositing thick beds of crystalline salt. These layers may be hundreds of meters thick, compressed and buried beneath sediments laid down later by rivers, wind, and new seas. What once drifted invisibly in water becomes stone. If you could travel back hundreds of millions of years, you might see shallow seas covering wide continental basins. Under intense sunlight and limited inflow, water would gradually retreat. As it did, salt concentration would rise until crystals formed along the bottom. Over time, those crystals accumulated, layer upon layer, recording cycles of evaporation and refill. When buried, salt behaves differently from many other rocks. Unlike granite or limestone, halite is relatively soft and ductile under pressure. Over long spans of time, thick salt deposits can deform plastically. Instead of fracturing sharply, they flow slowly, reshaping themselves under the weight of overlying layers. This movement can create salt domes, bulb-like structures that push upward through surrounding rock. A solid that moves, not quickly, but steadily. You might imagine deep underground layers compressed by kilometers of sediment. The salt beneath begins to rise because it is less dense than the surrounding rock. Slowly, almost imperceptibly, it presses upward. Over millions of years, this motion creates domes that distort rock strata above them. These domes sometimes trap oil and natural gas, shaping patterns of resource distribution. Salt domes are geological memory in motion. Mining practices developed around these ancient deposits. In some regions, vertical shafts descend into thick halite beds. Miners carve out large chambers, leaving pillars to support the ceiling. The walls of these underground rooms sometimes shimmer faintly under artificial light, reflecting the cubic geometry of the crystals. Other methods dissolve salt intentionally. Water is injected into underground deposits, dissolving halite and creating brine. The brine is then pumped to the surface and evaporated to recover purified salt. This technique leaves behind vast underground caverns. These caverns do not remain empty. Because salt is impermeable to fluids and relatively stable, some of these spaces are used to store natural gas, compressed air, or even strategic petroleum reserves. The same mineral that once formed from evaporated seas now holds energy resources deep underground. You might picture a cross-section of Earth's crust. Layers of sediment curve gently around a rising salt dome. Far below, an underground cavern carved by dissolution sits still, cool and dark. Within it, brine once flowed freely. Now it may hold compressed gas, stored in quiet equilibrium. Salt participates in Earth's slow architecture. It records ancient climates in layered deposits. It moves under pressure, reshaping rock formations. It provides space for modern storage systems. The crystal lattice remains the same, sodium and chloride in repeating cubic symmetry. Yet its geological role expands across epochs. The mineral does not announce its presence. It rests in buried basins, hidden beneath soil and stone. Yet its properties influence tectonic behavior, resource formation, and industrial design. From evaporated sea to halite bed, from halite bed to rising dome, from dome to cavern. Salt's journey through rock mirrors its journey through water and body. It dissolves, deposits, compresses, and shifts. The form changes with environment, but the internal structure persists. What was once part of a shallow ancient sea may now sit miles underground, bearing the weight of continents. And under that weight, it continues its slow movement, steady and patient, shaping the layers above without urgency. A mineral formed from water now shapes stone, and stone, in turn, holds its memory. Salt does not only shape oceans and rocks, it helps guide the movement of the climate itself. At the surface of polar seas, when temperatures fall low enough, ice begins to form. As water molecules arrange themselves into solid crystals, they exclude most dissolved salt. The forming ice becomes relatively fresh. The surrounding water, now containing the rejected salt, grows more concentrated. This process is known as brine rejection. The saltier water becomes denser than the water around it. Density increases not only with lower temperature, but also with higher salinity. As a result, this heavier brine sinks beneath the surface layers, descending slowly into the deep ocean. A freezing surface initiates downward motion. You might imagine a quiet Arctic evening. The sea is calm. Thin sheets of ice begin to spread across the surface. Beneath that forming ice, small pockets of concentrated brine drip downward, increasing the salinity of the water below. The motion is gentle but persistent. Over time, this sinking water contributes to large-scale ocean circulation. This circulation is often described as thermohaline, from thermo, meaning temperature, and haline, meaning salt. Differences in heat and salinity together determine density, and density differences drive movement. Warm water is generally less dense than cold water. Fresher water is less dense than saltier water. Where cold and salty conditions combine, the water becomes heavy enough to sink to great depths. In other regions, warmer or fresher water rises. These vertical exchanges connect ocean basins across continents. The global conveyor of deep currents redistributes heat, nutrients, and dissolved gases. Some segments of this circulation can take centuries to complete. A parcel of water sinking in the North Atlantic may not resurface in the Pacific for hundreds of years. Salt influences the speed and strength of these currents. If salinity changes significantly in key regions, density patterns shift. Increased freshwater input from melting ice or heavy rainfall can reduce surface salinity, making water less dense and slowing sinking. Reduced sinking alters the balance of circulation, which can affect regional climates. You might picture a map of the world's oceans, arrows tracing slow loops from polar seas to equatorial waters and back again. The lines represent movement shaped not only by wind and temperature, but by the quiet distribution of dissolved salt. The ocean does not move uniformly. It stratifies into layers, each with subtle differences in salinity and temperature. These gradients create stability in some regions and mixing in others. Life adapts to these conditions. Nutrients carried upward from deep waters support surface ecosystems. Carbon absorbed at the surface can be transported downward and stored for long periods. Salt participates in this planetary exchange. Sea ice formation and melting further modulate the cycle. When ice melts, it releases fresh water back into the ocean surface, reducing local salinity. When ice forms again, brine rejection resumes. The rhythm of freezing and thawing introduces pulses into circulation patterns. You might imagine a winter shoreline where the sea forms crystalline edges against rock. The ice appears solid and still, yet beneath it, salinity shifts are shaping density and guiding deeper flows. The climate system depends on gradients. Temperature differences create movement in the atmosphere. Salinity differences create movement in the ocean. Together, they regulate energy distribution across latitudes. The balance is delicate but resilient, maintained by continuous feedback between evaporation, rainfall, ice formation, and river inflow. Salt does not change the weather in a single day. It shapes long-term patterns. Its influence unfolds gradually through density differences and slow circulation. A dissolved ion drifting through seawater participates in currents that moderate coastal climates, influence storm tracks, and sustain marine ecosystems. From brine sinking beneath polar ice to deep currents crossing ocean basins, salt remains part of a quiet engine moving beneath the surface. A mineral in solution becomes a driver of planetary rhythm. Density guides motion. Motion redistributes heat. Heat shapes climate. And within each of these steps, sodium and chloride remain dissolved, steady and unannounced, guiding movement through subtle difference rather than force. Salt's role did not remain confined to preservation and ocean circulation. As societies grew more complex, its chemical properties became part of industrial systems. When dissolved in water and subjected to an electrical current, salt undergoes a transformation. In a process known as electrolysis, brine is separated into new substances. At one electrode, chlorine gas forms. At the other, hydrogen gas is released. In the remaining solution, sodium hydroxide is produced. This method, often called the chlor-alkali process, depends on the movement of ions through a membrane under applied voltage. Sodium and chloride separate again, not by water's polarity alone, but by electrical force. Chlorine produced in this way is used to disinfect water, helping control harmful microorganisms in drinking supplies. Sodium hydroxide, also known as caustic soda, is used in soap production, paper manufacturing, and many chemical syntheses. The same mineral once carried in caravans now participates in modern infrastructure. You might imagine a large, quiet industrial hall where rows of electrolysis cells operate steadily. Brine flows through chambers separated by membranes. A low hum from electrical current accompanies the slow formation of gas bubbles. The transformation is controlled, measured, continuous. Salt becomes chemical feedstock. In glass manufacturing, sodium compounds derived from salt lower the melting temperature of silica. This allows sand to fuse into glass at more manageable temperatures. The sodium acts as a flux, altering the physical behavior of the mixture. Transparent sheets and containers emerge from controlled heat and composition. On winter roads, salt is spread to prevent ice formation. As described earlier, dissolved salt lowers the freezing point of water. By scattering crystals across pavement, melting occurs more readily at temperatures where ice would otherwise persist. The grains dissolve in surface moisture, creating brine that resists freezing. You might picture a quiet morning after snowfall. The air is still. On the road, scattered crystals begin to dissolve as sunlight warms the surface. Thin layers of brine form, reducing ice and restoring traction. The mechanism relies on ionic interference with water's crystal structure. Salt also participates in water softening. In regions where groundwater contains high concentrations of calcium and magnesium, mineral buildup can occur in pipes and appliances. Water softeners often use sodium ions to replace these hardness minerals. Inside a resin bed, calcium and magnesium are exchanged for sodium, altering the composition of the water and reducing scale formation. The exchange happens invisibly. Water enters with one mineral balance and exits with another. The sodium concentration increases slightly, but the change reduces precipitation of unwanted deposits. Salt's solubility and stability make it suitable for large-scale handling. It can be transported as solid crystals, dissolved into brine, stored underground, or processed into derivatives. Its cubic lattice structure provides predictable behavior under many conditions. You might imagine conveyor belts carrying pale crystals towards storage silos. The crystals reflect faint light, uniform in shape. From there, they move into solution tanks, pipelines, or distribution networks. Even in industries far removed from food or ocean, sodium chloride remains present. Chemical plants rely on its ionic separation. Municipal systems depend on its derivatives for sanitation. Road crews distribute it seasonally. Manufacturers incorporate its components into materials used daily. Salt does not dominate these systems. It integrates quietly. The mineral that once shaped trade routes now supports electrical processes, public utilities, and manufacturing. Its properties, solubility, ionic charge, stability, make it adaptable across contexts. From electrolysis cells to glass furnaces, from resin beds to winter roads, salt moves through controlled environments shaped by human design. The underlying chemistry remains unchanged. Sodium and chloride separate, combine, dissolve, and conduct. A crystal mined from ancient rock becomes part of an electrical circuit. An ion drifting in brine becomes a disinfectant. The journey continues, guided by predictable behavior rooted in charge and structure. Salt's presence in industry reflects the same qualities seen in preservation and climate: balance, interaction, transformation. Quiet properties scale outward. A mineral shaped by evaporation now shapes infrastructure, steady and unannounced, within systems that operate day after day. Within the body, salt remains a matter of balance. Sodium is required in measurable amounts each day. It supports nerve signaling, muscle contraction, and fluid distribution. Health organizations often recommend moderate intake, generally suggesting that adults limit sodium to around 1,500 to 2,300 milligrams per day, depending on age and overall health. These numbers reflect an effort to maintain equilibrium rather than eliminate salt entirely. Too little sodium can disrupt function. When blood sodium concentration drops below normal levels, a condition known as hyponatremia may occur. Because sodium helps regulate water movement across cell membranes, low sodium in the bloodstream can cause water to move into cells. In the brain, where space is limited, swelling can interfere with normal signaling. Symptoms may include confusion or fatigue when levels fall significantly. The body responds early to prevent this shift. Thirst may increase. Hormones signal the kidneys to conserve sodium. Urine becomes more concentrated. These adjustments often correct mild imbalances before they become severe. On the other end of the spectrum, excessively high sodium levels in the blood, called hyponatremia, can cause cells to lose water. When extracellular sodium rises, water moves out of cells to restore osmotic balance. This may lead to cellular shrinkage and corresponding symptoms such as thirst or weakness. Again, the body compensates. Antidiuretic hormone regulates water retention. The sensation of thirst encourages fluid intake. The kidneys adjust filtration and reabsorption to restore stable concentration. Homeostasis describes this steady regulation. The term refers to the body's ability to maintain internal conditions within narrow limits despite changes in external environment. Sodium concentration in blood plasma is one of the most tightly controlled variables. Small deviations trigger corrective feedback. You might imagine a clear stream flowing through a narrow channel. If the water level rises slightly, overflow mechanisms guide it back within boundaries. If it falls, inflow increases. The channel remains stable not because nothing changes, but because adjustments occur continuously. Salt participates in this regulation quietly. Blood pressure is one area where sodium balance intersects with cardiovascular health. Sodium influences fluid volume in the bloodstream. Increased sodium intake can contribute to higher fluid retention in some individuals, potentially affecting blood pressure. The relationship is complex and varies among people, depending on genetics, kidney function, and overall diet. Moderation becomes the theme. Salt is necessary, yet excess may strain regulatory systems over time. The body can handle variation, but long-term imbalance may challenge its capacity to compensate. You might picture the interior of a blood vessel, smooth and elastic. Blood flows steadily. Dissolved sodium drifts among proteins and red blood cells. The concentration remains within a narrow band, supported by hormonal signals and kidney filtration. The balance is dynamic. Sweat loss during heat or exertion removes sodium from the body. Replenishment restores equilibrium. During illness, fluid loss may alter concentration. Medical care often involves adjusting sodium levels carefully, either through intravenous solutions or controlled intake. Salt is not simply added or removed. It is managed. The same ionic principles described earlier, osmosis, electrical gradients, fluid distribution, apply within this context. A shift in sodium concentration alters water movement. Water movement alters pressure and cell volume. Feedback systems detect these changes and respond. You might imagine evening settling in, the body at rest. Beneath the surface, kidneys filter blood, reclaiming sodium where needed. Hormones circulate quietly, adjusting channels in microscopic tubules. The system works without conscious direction. Salt's presence is steady but restrained. It supports function when balanced. It challenges function when displaced. The goal is not elimination, nor excess. It is equilibrium. From dissolved crystal to circulating ion, salt's role in health reflects the same pattern seen in oceans and preservation. A small difference in concentration can shift an entire system. Balance remains the quiet theme. Sodium, present in measured amounts, supports stability through constant regulation, guiding water and charge within narrow, life-sustaining limits. Salt appetite is not random. When sodium levels in the body begin to decline, a coordinated response unfolds. The kidneys detect shifts in concentration and activate hormonal pathways. One of the primary regulators is aldosterone, a hormone released from the adrenal glands. Aldosterone signals the kidneys to increase sodium reabsorption, conserving it rather than allowing it to pass into urine. At the same time, the brain becomes involved. Specialized regions monitor osmotic balance in the blood. When sodium falls or fluid balance shifts, neural circuits adjust perception and motivation. Foods that contain salt become more appealing. The threshold for detecting salty taste may lower slightly, making modest amounts feel more noticeable. The desire reflects physiology. You might imagine a long day of physical activity in warm weather. Sweat evaporates from the skin, cooling the body. Along with water, sodium leaves through sweat glands. As fluid loss continues, blood concentration shifts subtly. Hormonal signals increase sodium retention. Thirst grows stronger. Thirst and salt appetite are linked but distinct. Thirst primarily responds to water balance and osmolarity. Salt appetite responds more directly to sodium deficit. In many cases, both sensations arise together, guiding intake toward restoring equilibrium. The interplay is coordinated. If sodium levels are low but fluid levels remain adequate, the body may increase salt-seeking behavior without dramatic thirst. If water levels are low but sodium is sufficient, thirst predominates. These responses overlap, yet each addresses a specific imbalance. You might picture a runner pausing after exertion, reaching not only for water, but also for a lightly salted snack. The preference feels intuitive. Beneath that intuition lies a cascade of hormonal and neural adjustments. The kidneys remain central to this regulation. Every day, they filter large volumes of plasma, reclaiming most sodium through reabsorption in specialized segments of the nephron. Aldosterone increases the activity of sodium channels in the distal tubules, enhancing retention when needed. When sodium intake rises, hormonal signals decrease, allowing more sodium to be excreted. balance shifts gradually. Salt cravings can intensify under certain conditions. Prolonged sweating, dehydration, or specific medical states may amplify the desire for salty foods. In experimental settings, animals with induced sodium deficiency display strong preference for saline solutions they would normally avoid. The internal state reshapes taste evaluation. The same mechanism exists in humans, though often less dramatic. Evolutionary pressures likely shape this responsiveness. In environments where sodium was scarce, individuals capable of detecting deficiency and responding behaviorally would have maintained better fluid balance. Taste became a regulatory extension of internal chemistry. You might imagine early humans traveling through dry terrain. Access to mineral-rich sources might have been intermittent. Subtle shifts in appetite could guide attention towards certain foods or locations known to contain salt. Sweat also reflects adaptation. Human sweat glands excrete sodium, but the concentration can adjust depending on acclimatization. With repeated exposure to heat, the body becomes more efficient at conserving sodium, reducing losses over time. Hormonal regulation fine-tunes this response. Salt appetite is therefore flexible. It increases when needed. It subsides when restored. The cycle mirrors other homeostatic systems described earlier. Sodium levels influence hormone release. Hormones influence kidney function and perception. Perception influences intake. Intake restores balance. You might picture an evening meal after a day in the sun. A faint preference for savory foods feels natural. The body's internal chemistry guides choice without overt awareness. Salt craving is not excess by default. It is information. The same ions that move across nerve membranes now shape appetite signals within the brain. Electrical gradients support awareness of need. Behavioral adjustment follows. From aldosterone release to kidney reabsorption, from taste receptor sensitivity to conscious selection. Sodium remains part of a continuous feedback loop. A mineral dissolved in blood becomes a subtle shift in preference. Preference becomes intake. Intake becomes balance. And balance restores quiet stability within the body, guided by signals that rarely announce themselves loudly, yet operate with steady precision. Salt regulation is not unique to humans. Across the animal kingdom, different species have evolved strategies to manage sodium and water balance in environments that range from open ocean to arid desert. Marine animals live surrounded by salt water, a solution far more concentrated than their internal fluids. If they did nothing, water would leave their bodies by osmosis and salt would move inward. To survive, they regulate actively. Many marine fish drink seawater continuously. Specialized cells in their gills, often called chloride cells, pump excess sodium and chloride back out into the surrounding ocean. Their kidneys produce small amounts of concentrated urine to conserve water. The balance is maintained through constant ion transport across membranes. You might imagine a fish moving slowly through clear blue water. The sea around it contains far more salt than its bloodstream. Yet within its body, concentrations remain steady. Microscopic pumps in the gills exchange ions, maintaining equilibrium against the gradient. Freshwater fish face the opposite challenge. The water surrounding them contains far less dissolved salt than their internal fluids. Water tends to enter their bodies by osmosis, and salts tend to diffuse outward. To compensate, freshwater fish produce large amounts of dilute urine to remove excess water. At the same time, they actively absorb sodium and other ions through their gills from the surrounding water. The direction of regulation reverses. Marine fish push salt outward. Freshwater fish pull salt inward. Both rely on the same principles of osmosis and ion transport, yet their strategies differ depending on environment. Desert mammals encounter another variation. In dry climates, water is scarce. Sodium loss through sweat must be minimized. Some desert animals produce highly concentrated urine to conserve water, while maintaining sodium balance through efficient kidney function. Camels, for example, tolerate significant shifts in hydration without rapid collapse. Their physiology allows them to manage fluid distribution under extreme conditions. You might picture a desert landscape at dusk. The air is dry. A mammal moves slowly across the sand. Inside its body, kidneys adjust filtration to preserve both water and sodium. The balance is dynamic, shaped by environmental pressure. Reptiles and birds that consume seawater or salty prey have developed specialized salt glands. These glands, located near the eyes or nasal passages, excrete concentrated saline solutions. In seabirds, droplets of salty fluid may be seen dripping from the beak after feeding. This adaptation allows them to ingest salt water without disrupting internal balance. Salt glands act as auxiliary kidneys. They provide a secondary pathway for sodium removal, especially in species whose kidneys alone cannot concentrate urine sufficiently to offset seawater intake. You might imagine a seabird resting on a coastal rock. After diving for fish, it returns with prey that contains seawater. As it settles, small droplets of saline solution emerge near its nostrils, expelled by specialized glands. The ocean remains outside the body. Even insects show sensitivity to salt balance. Some species actively seek sodium-rich sources, such as damp soil or animal remains, to supplement low-sodium diets. Butterflies gathering at mineral-rich mud reflect the same underlying need described earlier in mammals. Across species, salt regulation reflects environment. Marine organisms push salt outward. Freshwater organisms pull salt inward. Desert species conserve both water and sodium. Birds and reptiles add specialized glands to assist. The mechanisms differ, yet the principle remains constant. Maintain internal stability despite external variation. You might picture a series of landscapes: ocean, river, desert, coastline, each inhabited by creatures adapted to its salinity. Within each body, sodium and chloride move through channels, pumps, and glands. The same ions drift through seawater and bloodstream, yet boundaries remain intact. Salt defines inside and outside. Life depends on preserving that distinction. From fish gills to seabird glands, from mammalian kidneys to insect behavior, sodium balance shapes survival quietly across ecosystems. The mineral that formed in ancient seas now moves through living bodies in countless forms, always guided by gradients and membranes. Environment changes. The need remains. And within that need, salt continues its steady work, maintaining balance in water-rich oceans and water-scarce deserts alike. Salt holds its shape because of attraction. When sodium and chloride meet, something simple and steady happens. Sodium gives up a single electron. Chlorine accepts it. That exchange leaves sodium positively charged and chloride negatively charged. Opposite charges pull toward one another, and that pull is strong enough to lock them into position. Not loosely, not randomly. Each ion settles into a repeating arrangement, forming a crystal lattice that extends outward in every direction. If you could shrink yourself down small enough to move through a grain of salt, you would not see chaos. You would see order. Positive, negative, positive, negative. Layer after layer. A quiet electrical rhythm repeating in space. This arrangement explains why salt forms cubes. The internal geometry is symmetrical. Each sodium ion is surrounded by 6 chloride ions. Each chloride ion is surrounded by 6 sodium ions. The pattern balances itself in 3 dimensions, and when the crystal grows large enough to see, its external shape reflects that inner structure. Edges, corners, flat planes, structure made visible. The forces holding this lattice together are electrostatic. They are not hooks or hinges, but fields of attraction between charges. The strength of this attraction is called ionic bonding. It is firm, which is why salt has a relatively high melting point, around 801 degrees Celsius. It remains solid under conditions that would soften or melt many other substances. And yet, that same structure can be undone with something as gentle as water. Water molecules carry slight electrical polarity. One side of each molecule is slightly positive. The other side is slightly negative. When salt touches water, the positive side of water molecules is drawn toward chloride ions, and the negative side is drawn towards sodium ions. Slowly, the water surrounds and separates them. The crystal does not collapse all at once. It loosens, ion by ion. What was once a rigid lattice becomes a solution of freely moving charges. If you were to watch salt dissolve in a clear bowl, you might see the edges of a crystal soften first. The corners fade. The solid form becomes less defined. Eventually, nothing remains visible, yet the ions are still present, suspended in the water, moving independently. Dissolving does not mean disappearing. In solution, salt allows water to conduct electricity. Pure water conducts very poorly. But when sodium and chloride ions move freely, they carry charge through the liquid. That movement of ions is what makes salt water conductive. Even oceans conduct because of this quiet dispersal. Salt also changes how water behaves at boundaries. When dissolved, it lowers the freezing point. Water molecules have a harder time organizing into the stable lattice required for ice. The presence of ions disrupts that pattern. As a result, seawater freezes at about -1.8 degrees Celsius, rather than 0. A small concentration shifts a physical threshold. This is why winter roads are treated with salt. Not to warm the surface, but to interrupt the formation of ice crystals. A subtle interference in structure prevents a larger system from locking into rigidity. Salt influences phase changes simply by existing in the solution. You might imagine a shallow tide pool at the edge of the ocean, the water still, the surface reflecting sky. Beneath that surface, dissolved ions drift invisibly, separating and recombining, interacting with water molecules that constantly rotate and form temporary hydrogen bonds. Nothing dramatic, no sharp edges, just motion at a scale too small to see. Salt, in its solid form, is rigid and geometric. In water, it becomes fluid and dispersed. The same particles arranged differently, the same charges behaving in new ways depending on their environment. Structure, separation, balance. What appears simple at a distance reveals layered behavior up close. And we will keep moving closer, slowly, one layer at a time. When salt dissolves, it does more than disappear into water. It begins to participate in a different kind of structure. In a solid crystal, sodium and chloride are locked into position, each ion held in place by surrounding opposites. In water, that fixed arrangement loosens. The ions separate and move independently, yet they do not drift without influence. Each sodium ion, carrying a positive charge, becomes surrounded by water molecules whose slightly negative oxygen ends turn inward. Each chloride ion, carrying a negative charge, becomes surrounded by water molecules whose slightly positive hydrogen ends orient toward it. Water does not simply mix with salt, it reorganizes around it. This surrounding layer is called a hydration shell. It is a temporary arrangement, constantly shifting as water molecules move and rotate. But it stabilizes the ions in solution. The lattice that once held the crystal together is replaced by a dynamic cloud of interactions. What was once rigid becomes fluid, yet still structured at a smaller scale. If you imagine a clear bowl of water sitting quietly on a table, light passing through it, nothing visible within it, that transparency hides countless movements. Sodium and chloride ions drift in gentle thermal motion. Water molecules form and break hydrogen bonds billions of times each second. Even in stillness, there is activity. Salt in water changes how water behaves as a system. When ions are present, they interfere with the ability of water molecules to align into the organized pattern required for ice. Freezing requires water molecules to form a repeating crystalline structure. Dissolved salt interrupts that arrangement. As a result, the freezing point drops. Seawater freezes at a lower temperature than fresh water, and the more salt present, the lower that threshold becomes. This small change affects entire environments. In polar regions, sea ice forms at the surface, but as it freezes, it rejects most of the salt. The forming ice becomes relatively fresh, while the expelled salt increases the salinity of the surrounding water. That saltier water becomes denser and sinks. This process contributes to deep ocean circulation, helping drive global currents that distribute heat across the planet. A grain dissolving in water connects to planetary motion. Salt also influences boiling. When dissolved, it raises the boiling point of water slightly. The presence of ions makes it harder for water molecules to escape into vapor. The effect is modest in everyday cooking, but measurable. A shift in phase behavior, simply from dispersed charge. In the body, dissolved salt shapes fluid movement at a cellular level. Water moves across cell membranes through osmosis, flowing toward areas of higher solute concentration. If the fluid outside a cell becomes too concentrated with salt, water leaves the cell and it shrinks. If the external concentration drops too low, water enters and the cell swells. Balance is not static. It is actively maintained. Blood plasma contains sodium at a tightly regulated concentration. The kidneys filter large volumes of fluid each day and selectively reabsorb sodium to maintain that range. Hormonal signals adjust how much sodium is retained or released. This regulation happens continuously, without conscious awareness. Even sweat carries dissolved salt outward. When it evaporates, faint mineral traces remain on the skin. Tears contain salt at levels that protect the eye and match the chemistry of surrounding tissues. Every fluid in the body carries ions that support electrical gradients and pressure differences. Salt in solution is invisible architecture. You might picture a shallow tide pool warmed by afternoon light. The surface calm. Beneath it, countless ions suspended between grains of sand and fragments of shell. The water looks simple, clear, undisturbed. Yet dissolved within it is a quiet framework of charge that shapes how organisms survive, how temperatures shift, how currents begin. Dissolving is not a loss of structure. It is a transformation from rigid order to mobile influence. Salt moves from crystal to current, from fixed lattice to flowing balance. The same particles, the same charges, behaving differently depending on their surroundings. Water does not erase salt. It gives it range. As salt moves through water, it becomes part of living systems. Inside the human body, sodium and chloride are among the most abundant ions in extracellular fluid. They do not sit in crystals. They move through blood plasma, between cells, along membranes, always carried in solution. The concentration is not random. Blood plasma typically contains sodium in a narrow range, close to 135 to 145 millimoles per liter. That range is maintained with precision because even small deviations can shift how water distributes itself between compartments. Water follows salt. If sodium levels rise outside cells, water moves outward to balance the concentration. If sodium levels fall too low, water moves inward. Cells depend on this gradient remaining stable. Too much swelling can disrupt structure. Too much shrinking can interfere with function. The balance is not static. It is continuously adjusted by the kidneys, which filter roughly 180 liters of fluid each day and reclaim most of the sodium before that fluid leaves the body. Salt helps define boundaries. Every cell is enclosed by a membrane that separates interior from exterior. That membrane contains proteins known as ion channels and pumps. One of the most important is the sodium-potassium pump. It actively transports sodium out of the cell and potassium into the cell, using energy derived from ATP. This pump maintains a difference in charge across the membrane. The inside of a resting cell is slightly negative compared to the outside, often around -70 millivolts. That small voltage difference is the foundation of nerve signaling. When a neuron fires, sodium channels open briefly. Sodium ions rush inward, driven by both concentration difference and electrical attraction. The membrane potential shifts rapidly, creating an action potential that travels along the nerve fiber. Once the signal passes, other channels open to restore balance. The sodium-potassium pump quietly resets the gradient, preparing the cell for the next impulse. Every sensation, every movement, every thought depends on these ion flows. Muscle contraction follows a similar pattern. Sodium gradients help initiate the cascade that allows muscle fibers to shorten. Without sodium, electrical signals would not propagate properly. Without that propagation, coordination would fade. Salt is not loud in its presence, but it is constant in its necessity. Chloride ions also play a stabilizing role. In many cells, chloride helps regulate electrical neutrality and fluid balance. In the stomach, chloride combines with hydrogen ions to form hydrochloric acid, which aids digestion. The same element that forms a gentle crystal in a bowl becomes part of a highly acidic environment when combined differently. Context shapes behavior. In sweat, sodium and chloride move outward through specialized glands. As sweat evaporates from the skin, it leaves behind faint mineral traces. This evaporation cools the body, preventing overheating. In tears, dissolved salt maintains osmotic balance and helps protect the surface of the eye. Tears taste slightly salty because their ionic concentration mirrors that of plasma. Salt moves where fluid moves. You might imagine blood flowing through narrow vessels, quiet and rhythmic. Within that fluid, sodium and chloride drift among proteins, glucose molecules, and dissolved gases. Nothing visible marks their presence, yet they shape how water distributes, how cells communicate, how pressure is maintained. The body works continuously to preserve this internal environment. Hormones, such as aldosterone, signal the kidneys to retain sodium when levels drop. Antidiuretic hormone influences water reabsorption, adjusting concentration without conscious effort. Thirst arises when osmotic sensors detect shifts, encouraging fluid intake before imbalance grows. These adjustments are subtle. They unfold gradually, maintaining equilibrium. Salt in the body is rarely noticed directly. It does not glow or pulse. It does not signal its own importance. It participates in gradients, in flows, in boundaries. It defines inside and outside. It permits electrical activity without drawing attention to itself. From a grain resting on a surface to ions drifting through blood, the same elements persist. Sodium and chloride do not change identity. They change arrangement. Within the body, the movement of salt becomes electrical. At rest, every nerve cell maintains a quiet difference between its interior and the surrounding fluid. Sodium ions are more concentrated outside the cell. Potassium ions are more concentrated inside. This uneven distribution is not accidental. It is created and preserved by the sodium-potassium pump, which moves sodium outward and potassium inward against their natural gradients. This process requires energy, but it establishes the foundation for signaling. The membrane itself acts as a barrier, thin and flexible, embedded with proteins that control ion flow. When a neuron is not actively sending a signal, the inside remains slightly negative compared to the outside. This resting membrane potential reflects a balance between permeability and charge. The difference is small in voltage, yet essential. When a signal begins, sodium channels open briefly. Sodium ions rush inward, drawn by both the electrical gradient and the concentration difference. The membrane potential shifts rapidly toward the positive. This change travels along the length of the neuron as a wave, a coordinated opening and closing of channels. Once the wave passes, potassium channels open, allowing potassium to move outward. The original balance is restored. The signal is temporary. The gradients remain. Salt provides the charge carriers. If sodium were not present in the extracellular fluid at appropriate levels, this rapid change could not occur. Electrical signals would weaken or fail. The coordination between neurons would become unstable. The brain's communication depends on ions moving across microscopic distances with precision measured in milliseconds. Muscle tissue follows a similar rhythm. When a motor neuron signals a muscle fiber, sodium channels open along the muscle membrane. This triggers a cascade inside the cell, leading to the release of calcium from internal stores. Calcium allows contractile proteins to slide past one another, shortening the muscle fiber. After contraction, ions are pumped back into place and the fiber relaxes. Contraction and release. Impulse and reset. Salt supports both. You might picture the interior of a nerve cell as a narrow pathway extending from one end to the other. Along its surface, tiny gates respond to changes in voltage. Sodium ions move inward in coordinated sequence, like a ripple traveling across a calm surface. Nothing visible marks the event from outside the body, yet inside, entire networks respond. Even the heartbeat depends on these gradients. Specialized cells in the heart generate rhythmic electrical signals without conscious direction. Sodium and calcium movements initiate each contraction. Potassium helps restore resting conditions. The cycle repeats, steady and measured. The heart's rhythm is ionic at its core. The brain's activity is ionic at its core. Salt remains dissolved, unseen, yet central. The concentration of sodium in the extracellular fluid must remain stable to preserve this electrical reliability. If sodium levels fall too low, nerve cells may struggle to maintain gradients. If levels rise too high, water shifts across membranes, altering cell volume and pressure. The body responds through thirst, kidney adjustment, and hormonal signaling long before major imbalance develops. These corrections are quiet. They occur continuously. You might imagine a dimly lit evening room, calm and still. Beneath the surface of the body, thousands of electrical impulses move along nerve fibers each second. Sodium ions cross membranes and are carried back to starting positions. Pumps operate steadily. Channels open and close with precision. The electrical activity of the nervous system does not feel like electricity. It feels like perception, movement, memory. Yet at its base, it is movement of charged particles across membranes thinner than a fraction of a hair. Salt does not create thought on its own. It allows the conditions under which thought becomes possible. It establishes gradients. It carries charge. It maintains difference so that change can occur. A system of balance makes response possible. Without contrast, no signal. Without gradient, no movement. The ions that once formed a rigid cube now drift through extracellular space, entering and exiting cells, resetting differences that allow the body to remain aware and responsive. Solid crystal, dissolved ion, electrical current. The form changes, the function deepens. Salt becomes motion, and motion becomes experience. Every living cell exists within a boundary. The cell membrane is a thin, flexible layer made primarily of lipids arranged in a double sheet. This bilayer separates the interior of the cell from the surrounding fluid. It is selective, allowing certain substances to pass while restricting others. Water can move through specialized channels. Small, uncharged molecules may diffuse across slowly. Charged particles, including sodium and chloride, require controlled pathways. Salt becomes central at this boundary. Sodium and chloride ions cannot freely cross the lipid membrane because of their charge. Instead, they pass through protein structures embedded within the membrane. These structures, known as ion channels and transporters, open or close in response to specific signals. The membrane is not simply a wall. It is an active interface. On one side lies the cytoplasm, with its own ionic composition. On the other lies extracellular fluid, also carefully regulated. The difference in sodium concentration between these two compartments is not incidental. It is maintained deliberately. Outside most cells, sodium concentration is relatively high. Inside, it is lower. This gradient creates stored potential energy. When sodium channels open, sodium ions move inward along their concentration gradient, carrying electrical charge with them. This movement can trigger changes in membrane potential, initiating signaling events described earlier. The gradient itself is structure. You might imagine a still lake divided by a narrow gate. On one side, the water level is slightly higher. If the gate opens, water flows through, driven by difference. In cells, the water level is ionic concentration. The gate is an ion channel. The flow is diffusion guided by charge. Diffusion gradients are not static lines on a diagram. They represent real differences in particle distribution. Sodium ions cluster more densely outside the membrane. Chloride may follow its own gradient depending on cell type. Potassium predominates inside. Together, these distributions create electrical charge balance. Charge must remain balanced overall. Although gradients exist across membranes, total positive and negative charges within compartments are matched by counterions and proteins. The membrane potential arises from localized separation of charge at the boundary, not from overall imbalance in bulk solution. Salt participates in this separation. Sodium and chloride help define extracellular charge environment. Their distribution influences how other ions behave. Even small shifts in concentration can alter membrane excitability. You might picture a microscopic cross-section of a cell membrane under magnification. Embedded proteins form channels like narrow tunnels. On one side, sodium ions drift. On the other, potassium ions move more slowly. The membrane appears thin and delicate, yet it supports complex electrochemical relationships. This invisible architecture sustains life. Without ionic gradients, cells would lose their ability to respond to stimuli. Muscles would not contract. Neurons would not signal. Even basic transport of nutrients relies on coupled ion gradients, where the movement of sodium inward powers the uptake of glucose or amino acids against their own concentration differences. Salt, dissolved and dispersed, becomes scaffolding. It does not form beams or walls, yet it defines space through gradient. It shapes where water moves and how charge distributes. It allows membranes to function as selective barriers rather than passive dividers. The same sodium chloride that once formed a crystal lattice now forms a distributed network of electrochemical tension across billions of cells. You might imagine a quiet evening room. Within the body, countless membranes maintain differences in concentration measured in millimoles. Pumps operate steadily. Channels open briefly, then close. Charge shifts, then resets. The system holds. Salt does not stand out. It dissolves completely in solution. Yet it remains measurable, present in specific concentration ranges that define internal stability. Cellular boundaries depend on that presence. From extracellular fluid to intracellular cytoplasm, gradients persist across membranes thinner than a whisper. Salt becomes invisible architecture, maintaining separation and connection at once. A boundary exists. Across that boundary, ions move. In that movement, life continues. Salt often appears simple when viewed as a crystal, yet its influence is rooted in stability. Chemically, sodium chloride forms one of the most stable ionic structures found in nature. Each sodium ion carries a positive charge. Each chloride ion carries a negative charge. When they combine, they arrange into a repeating cubic lattice, where each ion is surrounded by oppositely charged neighbors. This structure minimizes energy. It is balanced and predictable. The crystal rests in equilibrium. When dissolved, that stability changes form, but not principle. The ions separate, yet remain stabilized by water molecules that orient around their charge. Whether solid or dissolved, salt seeks balance. In crystal form, it balances charge within a rigid lattice. In solution, it balances charge through hydration shells and electrostatic interaction. Stability is not rigidity alone. It can be dynamic. In biology, equilibrium refers to steady internal conditions maintained through constant adjustment. Sodium concentration in blood remains within narrow limits. Ion gradients across membranes persist despite continuous ion movement. The system does not freeze in place. It corrects itself repeatedly. Salt participates in this equilibrium. Without sodium and chloride, fluid balance would shift unpredictably. Electrical signals would weaken. Cells would lose structure. The stability of organisms depends on maintaining ionic differences within tight boundaries. Beyond the body, the ocean reflects a similar theme. Average ocean salinity has remained relatively consistent for tens of millions of years. Rivers bring dissolved minerals into the sea. Sedimentation, mineral formation, and tectonic processes remove them. The result is a long-term steady state. The ocean does not grow indefinitely saltier. Inputs and outputs counterbalance over geological time. You might imagine standing at the shoreline, watching waves move rhythmically across sand. Each wave carries dissolved sodium and chloride. The concentration varies slightly with rainfall or evaporation. Yet the overall salinity remains remarkably stable across vast regions. Climate systems exhibit inertia influenced by salinity. Thermohaline circulation, driven partly by salt concentration, moves slowly and persistently. Deep currents may take centuries to complete a cycle. Changes occur, but gradually. The presence of salt contributes to density gradients that resist rapid disruption. Stability emerges from balance of forces. In chemistry, equilibrium describes a state where forward and reverse reactions occur at equal rates. In physiology, homeostasis describes similar steadiness. In oceans, salinity balance reflects exchange between rock, river, and sea. Salt becomes a regulator across scales. You might picture a scale balanced at its center. On one side, river input. On the other, sediment removal. On one side, sodium intake. On the other, renal excretion. On one side, brine rejection. On the other, freshwater inflow. The mineral itself does not exert intention. Its properties create conditions under which balance becomes possible. Even industrial systems rely on predictable salt behavior. Electrolysis cells operate consistently because sodium chloride dissociates reliably in water. Road de-icing depends on its known freezing point depression. Water softening depends on consistent ion exchange. Predictability supports stability. You might imagine a quiet laboratory bench where a small beaker of saline solution rests undisturbed. The solution appears clear and still. Within it, ions move randomly, yet overall concentration remains unchanged. Dynamic motion coexists with macroscopic steadiness. Salt exemplifies this principle. At the molecular level, ions vibrate, diffuse, interact. At the system level, concentration remains steady. In oceans, currents move, ice forms, rain falls. Yet average salinity endures. In bodies, ions cross membranes thousands of times per second. Yet plasma sodium remains tightly regulated. The structure beneath these patterns is invisible, but it is measurable. A difference of a few millimoles alters physiology. A change in ocean salinity shifts density and current strength. The numbers remain small, yet their influence extends widely. Salt's role as regulator reflects its dual nature. It dissolves easily, allowing mobility. It forms stable crystals, allowing storage. It separates and reunites, yet always returns to balance of charge. From chemical lattice to climate inertia, from cellular homeostasis to oceanic equilibrium, salt embodies steadiness through interaction. It does not demand attention. It maintains proportion. And in maintaining proportion, it supports systems that persist quietly across scales, linking microscopic stability to planetary rhythm. Long before mountains rose into their present shapes, long before forests spread across continents, the oceans already contained salt. Early in Earth's history, as the planet cooled and water condensed to form the first seas, dissolved minerals began to accumulate. Volcanic activity released gases and compounds into the atmosphere and onto the surface. Rain interacted with newly formed rock, dissolving ions and carrying them into basins where water collected. Over immense spans of time, sodium and chloride became part of the earliest oceans. Salt was present before complex life emerged. The first living cells are thought to have arisen in aquatic environments where dissolved ions were already part of the surrounding medium. The chemistry of those early seas shaped the chemistry of life itself. Modern cells still maintain internal ionic compositions that reflect ancient conditions. The balance of sodium, potassium, and chloride within organisms may echo those early environments. You might imagine a shallow primordial sea under a faint young sun. The water is warm. Dissolved minerals drift invisibly within it. No fish swim yet, no birds fly overhead. Yet within this saline solution, chemical reactions unfold that eventually give rise to membranes, metabolism, and replication. Life emerged in water that contained salt. As continents shifted and climates changed, oceans expanded and contracted. Inland seas formed and evaporated, leaving thick halite deposits that would later become buried beneath sediment. Glacial cycles altered sea level. Tectonic plates rearranged coastlines. Yet throughout these changes, ocean salinity remained within a relatively narrow range. This stability spans deep time. Over hundreds of millions of years, the average concentration of dissolved salt in the open ocean has fluctuated modestly, but remained broadly consistent. Input from rivers has been balanced by removal through sedimentation and mineral formation. The ocean acts as a long-term reservoir, integrating countless small processes into steady composition. You might picture a timeline stretching backward across epochs. Dinosaurs walk along ancient shorelines. Ice sheets advance and retreat. Coral reefs rise and erode. Through each era, waves continue to move across saline water with familiar concentration. Salt becomes continuity. Even as species evolve and vanish, sodium and chloride remain dissolved in similar proportions. Marine organisms adapt to this consistency. The internal chemistry of living cells reflects evolutionary accommodation to stable salinity. In this sense, salt is a companion of life. It was present at life's beginning. It remains present now. It moves through oceans, through rock, through bodies. Yet its fundamental behavior does not change. Sodium retains its positive charge. Chloride retains its negative charge. Their attraction forms crystals. Their dissolution forms solutions. Deep time reveals repetition. Evaporation leaves deposits. Tectonics bury them. Uplift exposes them. Weathering dissolves them again. Rivers return ions to sea. The cycle unfolds across geological eras. You might imagine standing on a present-day shoreline, holding a grain of sea salt between your fingers. That grain may contain sodium and chloride that once circulated in ancient oceans inhabited by organisms long extinct. The crystal lattice forms again and again, independent of the era. Salt links past to present. Its constancy provides a backdrop against which life changes. The ocean's salinity supports marine ecosystems, generation after generation. The chemistry inside cells reflects ancient adaptations. Even halite deposits record episodes of evaporation millions of years old. The mineral does not evolve. Life evolves around it. Salt remains chemically simple, yet temporally vast. It accompanies tectonic shifts and biological innovation without altering its identity. From primordial seas to modern oceans, from buried deposits to dissolved ions drifting beneath waves, sodium and chloride persist. A crystal resting on a table carries deep history. A dissolved ion in seawater connects to epochs beyond memory. Salt moves through time as quietly as it moves through water, present, stable, continuous. Across billions of years, it has remained part of Earth's surface and part of life's internal chemistry. Ancient oceans gave rise to cells bathed in saline solution. Those cells multiplied, diversified, and formed organisms that still depend on controlled salt balance. Through deep time continuity, salt endures, steady companion of water, rock, and life itself. Salt dissolves easily. A crystal placed in water disappears within moments, its edges softening, its sharp geometry dissolving into transparency. To the eye, it seems gone. The surface becomes clear again, yet measurement reveals that nothing has vanished. Sodium and chloride remain present, dispersed evenly through the liquid. Invisible does not mean absent. Throughout this exploration, salt has shifted forms. It has been crystal and brine, deposit and current, cellular gradient and ocean reservoir. In each context, it operates quietly. Rarely does it stand at the center of attention. It integrates into systems already in motion. In the body, salt rarely announces itself. There is no sensation when plasma sodium sits at its proper concentration. No awareness of kidneys filtering and reclaiming ions. No conscious recognition of membranes maintaining gradients across billions of cells. Stability feels like nothing at all. Salt enables that feeling. You might imagine sitting beside a calm shoreline at dusk. The tide moves gently inward and outward. Beneath the surface, dissolved sodium and chloride drift within currents shaped by density and temperature. The sea does not declare its salinity with sound. It simply contains it. Structure beneath awareness defines many essential systems. Oxygen diffuses into blood without ceremony. Gravity holds feet to ground without sensation. Salt maintains electrical gradients without visible trace. The most necessary elements often operate quietly. When salt dissolves, it gives up its visible shape yet retains its influence. The cubic lattice vanishes, but ionic presence persists. In that presence, water behavior changes. Freezing points shift. Osmotic gradients form. Electrical signals become possible. A mineral becomes condition. You might picture a glass of water resting on a table. It appears clear and still. Dissolved within it may be small amounts of sodium and chloride. The liquid looks simple, yet within it ions move constantly, interacting with water molecules, creating hydration shells responding to temperature. The architecture is molecular. Cells depend on gradients across membranes. Oceans depend on stable salinity to maintain density-driven circulation. Industrial systems depend on predictable ionic behavior. Each relies on salt's properties without calling attention to them. Salt does not demand focus. It supports quietly. Even the sense of taste fades quickly. A pinch of salt on the tongue creates momentary perception. Then it blends into broader flavor, enhancing rather than dominating. Its presence becomes integrated. Stability often lacks spectacle. The body's internal sodium concentration remains within narrow limits day after day. The ocean's average salinity persists across centuries. These conditions allow change elsewhere. Without stable baselines, fluctuation would overwhelm. You might imagine a vast structure built upon a steady foundation. The foundation is rarely seen once the building stands. Yet it supports every wall and beam. Salt functions similarly within fluid systems. It defines interior from exterior. It allows charge to separate briefly and then restore. It lowers freezing point, enabling winter roads to clear and polar seas to cycle. It draws water in preservation and holds water in plasma. Throughout, it remains measurable but unseen. The essential often resides beneath notice. Salt dissolves yet remains. Its ions distribute evenly, integrating into systems that require no spotlight. A mineral that once formed in ancient seas now moves through modern bodies and oceans with the same quiet behavior. You might close your eyes and consider the steadiness beneath daily life. Breath moving without command, heartbeat continuing without thought, tides shifting under moonlight. Within each of these, subtle gradients persist. Salt stands among those gradients, invisible but constant, an enabler of balance rather than a spectacle. It forms structure without demanding attention. It maintains difference without disturbance. And in doing so, it supports systems that feel effortless, even though they depend on precise and continuous regulation hidden just beneath awareness. Salt rests quietly in so many places. It drifts through oceans that move in slow planetary rhythm. It circulates through blood in carefully measured concentration. It lies buried in rock layers formed from seas that vanished long ago. It dissolves into soups, into tears, into rain that once rose from the surface of the sea. Most of the time, it goes unnoticed. The body maintains its sodium balance without ceremony. Cells hold their gradients across delicate membranes. Currents move beneath the ocean's surface, guided in part by dissolved ions. Roads clear after winter snowfall because crystals alter how water freezes. Preservation slows decay because salt shifts the direction of water. A small mineral threads through each of these systems. You might imagine the surface of the ocean at night. The horizon fades into darkness. Beneath that surface, salt remains suspended, steady in concentration, participating in currents that will move for years before returning to the same latitude. Nothing urgent, nothing loud. Within the body, kidneys filter and reclaim sodium as you rest. Membranes hold their charge differences. Nerve cells reset after each signal. The balance continues quietly. Salt dissolves, yet it remains. It forms crystals, yet it flows. It disappears from sight, yet its effects are measurable in freezing points, in electrical potentials, in density differences across basins. Essential things often live in the background. They do not draw attention because they are constant. They do not demand recognition because they rarely fail. Stability feels simple, precisely because it is sustained so carefully. As you settle now, perhaps noticing your own breath moving gently in and out, consider the steady chemistry within you. Sodium and chloride drifting in plasma, gradients held across membranes, water distributed with quiet precision. Beyond you, oceans continue their slow exchange with atmosphere and rock. Rain will rise and fall. Rivers will carry minerals back to sea. Salt will accumulate in flats where water recedes and crystallize in deposits that may rest for millions of years. The cycle continues without announcement. A grain of salt may seem small, almost weightless in the palm. Yet within that grain lies a lattice shaped by charge, a history tied to ancient oceans, and a role that extends from cell to climate. Tonight, salt remains where it has always been, in water, in rock, in living systems, steady and unassuming. Invisible structure, measured balance, quiet continuity. And as the systems it supports move softly onward, you can allow your thoughts to drift just as gently, carried on rhythms that require no effort, resting in the steadiness of things that persist without needing to be seen.